Okay, let's get started. I want to welcome everybody to the final presentations of Perspectives in Assistive Technology. Students have been working very hard over the course of the quarter, and this is their presentation finale. So we'll start with last Thursday when Ralph Hotchkiss talked. Does anybody have any observations that are lingering in their mind that they'd like to bring up or talk about or have a question? I should mention that Ralph has been doing that wheelchair project for a long time, and his presentation basically highlighted the history of that project. As a person who consolidated these wheelchair designs from around the world into the one design that you saw there, and made it manufacturable in these developing countries for $200. So he deserves a lot of credit for that effort over many years, over many miles and countries. So it's really sort of amazing. So the class went earlier this year to the Magical Bridge Playground, and I'm happy to let you know that the grand opening is on April 18th, and everybody's welcome to attend. It's on a Saturday, so if you can make it, it'll be awesome. You can see the playground open and not in the midst of being under construction, so check that out. Okay, today's forums include the scoring sheet, so everybody should have one of those. Everybody's welcome to score. Just make sure you put down whether you're a student or faculty member, and this fellow here gets a form as well. Do you need a pen? Oh, you already got a form. I'm sorry. Okay, and another important form is this sign-up sheet for food on Thursday. This is when we're having the project presentation, so all the students who are going to be presenting today will bring their projects, and we'll meet out by Gibbons Grove after we convene in the classroom. So I'm going to supply the food from the treehouse. So we got your choice of pizza, a slice of pizza, a burrito, and drinks. So at the break, if you haven't signed up yet and you're going to be here on Thursday, please do that. For folks who have been with the course throughout the quarter, and for one reason or another, these are community members or students who are not going to be able to make it on Thursday, I have a course evaluation form. See me at the break to pick one of those up. I really want to know how well the course worked out for everybody, so it's important that you fill those out. Again, it's for community members and students. Okay, so this is for Thursday. We're going to meet in the classroom. After we fill out these evaluation forms, all the students and everybody are going to go out to the Grove, and I'll go out with the food. I'll have tables that you can set your projects up on. You students have a team to check out, have an opportunity to check out what every other team has done, and community members, can view all the projects. So this is an opportunity that we don't have when you're doing presentations, the opportunity to get up close and ask specific questions. So this is a chance for you for students to invite the people that you work with to see your project if they're not here now. And be sure while you're inviting them that you thank them for helping out with your project. Okay? That's Thursday. So for your project on Thursday, it should be functional, but we all realize that in 7 or 8 weeks you don't have a whole lot of time to make it market ready. So community members should think about that when they're evaluating the projects. You should have a plan if things don't work out quite as you expect it to, so make sure you have an alternate way of showing your project off. You can certainly add a logo. It could be your team logo or a Stanford logo, And what's really important is we all realize that it's a short amount of time, so you shouldn't apologize for things you haven't gotten to yet. But you can certainly talk about them as if you were going to be continuing the project. So mention future plans. And remember, everything is a prototype. You can prototype, for the rest of your life. So yesterday we saw the introduction of a brand new prototype, the Apple iWatch. I'm sure there's going to be many versions of those. So, okay. For students working on team projects, there's still some work to do. You have a final report and individual reflection to hand in. They're due Monday, but I realize that this is a busy time for students, and so if Monday doesn't fit your schedule because of finals and other things, you can request an extension for a few days. And you email the files to me in Word or PDF formats. Any questions on that? Excellent. For students working on projects, save all your receipts. That's the only way I can reimburse you. Select one member of the team to be who will be reimbursed. Going through this process of reimbursement takes a lot of time and administrative costs, so it doesn't make sense for each team member to submit their own reimbursements. I want to make it clear that shop passes are like books. They're not reimbursable, and neither is the mileage for your car. And I'll send out detailed instructions on this reimbursement process. Okay, there's a few of you who have still need to make up missed lectures. Please do that at your earliest convenience. Look at the material from the from the presentation you missed, and arrange to meet with me to discuss that. Okay. Pass this form back. Okay. So you might have got an email about the Registrar's online course evaluation, and the registrar, this encourages students to complete these online forms to evaluate the course and the instructor. They're open until the 28th of the month. You can review the results from previous evaluations online on Access. The motivation for you as a student is that you get your grades early as soon as the instructor sends them in. I can give you the grade just as even faster than that, because I'll be the one entering it. And if you have any questions, there's a web page to go to that talks about that. And I'm going to have something important to say about this process on Thursday, so stay tuned. So here we go. So students have been working on projects that address a problem experienced by a person with a disability or an older adult. They've been working for 7 weeks or so, working on a device or software to meet the problem. So these forms are for you to evaluate how well they did. And again, it's not, you shouldn't evaluate them as a commercial product. So please submit your score suggestions and comments, and I'll be passing these out to the individual teams so they'll see your comments. It's a part of the learning process. So this is the order of presentation, which matches the order on the scoring sheet. So without further ado, let's invite up Team Smith. Or are you going to stand?
I'll stand. Okay. Hi, my name is Eric Smith. I'm a junior studying mechanical engineering. I've been working in the past quarter on the Magical Bridge project. And for the next 8 minutes, I'll be introducing you to the park map that I've made in collaboration with the Magical Bridge Playground. If you came on our field trip, you may remember the Magical Bridge Playground is a brand new, fully ADA compliant and fully inclusive park in Palo Alto. By inclusive, I mean that kids of all abilities can come and enjoy the park. Part of that means that it needs to be navigable by all. I was immediately excited by the subject and was eager to see what the project entailed. And this is where Alenka Villarreal comes in, the founder of the Magical Bridge Playground. She asked me to build a 3D park map and that can be read by those who are blind or visually impaired. The map will give kids the idea of the layout of the park before they venture in to have safe fun. Alenka and I met several times over the past quarter to establish project goals and address the necessities of the park, which I'll talk about now. By looking at this map, we can get a quick grasp of the layout of the park. But this isn't true for someone who's blind or visually impaired. So what we need is some way for anyone who is visually impaired can get a layout of the park. What we decided we would build a large map for the entry plaza of the park right here. They can give everyone an overview of the park from the very beginning. Right now, the park has these pedestal maps placed throughout the park. The user goes, although they look nice, these are flawed in that they're out of date and without any tactile writing for those who are visually impaired. Here, I have scans of my logbook of the brainstorming process and selection process aimed to improve the situation from the previous slide. I spend a lot of time and effort to consider all types of materials I could potentially make my map out of. Some of these ideas were layered acrylic, formed plastic, or clay. Having established that acrylic layers would be the most practical approach, I began prototyping. My first steps in the build progress were these prototypes. What I learned from them helped me work through kinks and ensure that the map would come together well in the end. In this one, I tested out a lettering method that I ended up not using. In this one, I glued two pieces together and then broke the joint to see how strong the bind was. And in this one, I made a full mock-up of the map out of paper just to make sure that all the geometries are correct and that the layers worked nicely together. After prototyping, I was confident enough to build my fully layered map, and I'm pleased with the results. My final design was heavily dependent on laser cut parts, so I had to spend a lot of time tweaking this file right here. This is an Illustrator file of the shapes of the park. Fortunately, laser cutting itself is not too difficult and can produce finished products that look professional relatively easily. The cost of the project turned out to be $160, which was very close to my original estimate. Also, my favorite part of the map is the function of the text. Users can go throughout the park, run their fingers over the park, and be able to read the text and follow the path of the park and see which zones correspond to which text. Obviously, safety is a very important option being at a kids park. So kids will be rubbing their hands all over this, and I've got to make sure that all the edges are clear of any burrs or sharp pieces. And here's a time lapse of a video I made of the build progress of my latest prototype. In the video, I'm using acrylic cement, which is a liquid that chemically welds acrylic on top of each other. So it should fly by. So here's the main path that runs throughout the park. I had to put that one down first so that everything else was correctly placed out. on top of it. And there's the zones I'll put in. Not without the masking tape off yet. So all of this that's on the board right now is the first layer of acrylic, and I'm going to start on the second layer. It's tricky because you have to put all the letters of the E's and all the O's back into place, which is kind of a pain.
You did this all at one sitting?
Yeah, it was like an afternoon and a half. So those are all the walls, so you can run your finger along and not run off the path. You'll know where the edge of the path is. This is the beginning of the tree house. A lot of moving around and making sure it's all in the right place, obviously. Now the features of the park are coming on in orange. So that'll be like the spinny things, the swings, the slides. There we go. Go back to the last slide. So looking forward, I'm excited for the opportunities to build more of these. With the same file that I made, I could use a ShopBot, which is this machine right here, and create something 3 times the size out of wood, which I think would also be really impressive. It would also give me the opportunity to perfect some of the issues that came up while I was building this prototype. Although I thoroughly enjoyed the project, and I'm proud of what I've accomplished. And thank you guys very much for listening.
Okay, we're not going to take questions, but Eric will be at the demonstrations on Thursday, so that'll be your chance to check this out. So next is Dukes of Hazzard. When you're ready.
All right. Hello, we are the Dukes of Hazzard. We have Dan, Stuart, Tom, my name's Andres. And our project this quarter was to design improved hand controls. So a quick agenda, we're going to give you a little background of what hand controls are, who uses them, what the problems are with current hand controls and what goals we had to improve them, our design process for meeting these goals, what our initial prototypes were. We'll look at our current model and our future improvements. So hand controls are basically metal rods that attach to the brake and accelerator pedal in a car, extend beneath the steering column and allow the driver to operate the pedals with their hand. There are basically 2 types. You have permanent installation controls and temporary travel or portable controls. Our project focused on the portable controls because there's a lot more room for improvement. Now, who might use these? Well, basically anyone with limited or no function in lower extremity. This could include anyone that's paraplegic, amputee, or has degenerative or muscular diseases. A study in 2002, and I believe the only study as of yet, done by the U.S. Department of Transportation, estimate there's about 88,000 people in the United States that use hand controls.
So when I use my current set of travel hand controls, I have to get down on my knees in the parking lot, and I have to stick my head and my hands down into the footwell of the car, I have to take the lower assembly and physically clamp it on to the brake and to the accelerator. And this process takes a while. Once that's completed, I hop up into the driver's seat, and then I have to attach the upper assembly, secure it with a strap around the steering column, and then make sure it's all the right size, and then it's ready to go. The total process altogether takes just under 8 minutes. 5 of those minutes, I'm actually outside the car. If it's raining, I'm getting rained on. If it's really hot, I'm kneeling down on the hot asphalt. And then the disassembly is not too bad, but it still takes a minute and a half, depending on the structure of the car. Sometimes I can do it from the driver's seat. Sometimes I need to get back out and kneel down onto the pavement again.
So our goals for improvement moving ahead were to firstly reduce the time it takes to assemble and disassemble the controls. Most importantly, we wanted to allow the user to tighten the controls from within the car while seated. And we also wanted a universal design because these controls are meant for traveling, so you need to be able to use them on virtually any car. Our secondary objectives were to retain the extendable length and collapsible design, which makes them easy to transport. And we don't want them to really require fine motor skills, so basically anyone can use them. So here we have a couple images of our initial brainstormed ideas. We tried to be pretty open-minded. We thought of maybe a pulley design for tightening, using a claw or magnets to clamp to the pedals. The only one we decided on was this lasso design. And basically this achieves all of our 3 main goals right off the bat. The cord is flexible, so you can fit it on any pedal, making it universal. You can easily tighten it, and you can tighten from a distance. Our first prototype was just out of PVC, quick and dirty, to give us more of a visual representation of what we wanted and some preliminary functional ideas. Our second prototype actually incorporated the controls that Dan already has, and you can see we added our cord onto the bottom and then a secondary rod off one of the ends with our ratcheting device on top. Now this second shaft was because at first we were having problems with an imbalance in moment, but you'll see in the final product we were actually able to move our ratcheting device back onto the main shaft. But this prototype was really good for showing us what problems that we would have to eventually overcome and allowed us to test the function of our device a lot better.
So, moving on from this, we really liked the design that we had, we liked the mechanisms that we were working with, and we liked the tensioner that we were dealing with. So we got down and dirty into the shop, did some basic sheet metal working, some bending. We got on the mill a little bit, on the lathe a little bit. We got a lot of our processes done really early, and we came up with this product at the end. You can see that the tensioner is up a little bit on the center rod, and we were able to get the cord off of that side and onto the center rod. You can go ahead and play the movie. On these controls, you can also see that we have Dyson on the end block. We've diced them on the end block that grips really nicely with the pedal. Having the tensioner up on the rod, it's up around 8 inches. That gives you the ability to be tightening the prototype on the pedal without actually having to get down next to the pedal. So that allows you to stay up in your seat. As you can see here, what Dan is doing, he's looping the cord on the pedal. He's looping the cord on the pedal, and then he's cinching it up and tightening it with that lever action for the ratcheting mechanism. Gets it nice and tight on the pedal. There he's putting it on the brake. He does the same thing, just loops the cord over it. The Dyson grips down nice. It's got a good feel. It doesn't move around a whole lot, and we have an even moment for what we're doing there. He gets it all tight, and then he's able to put on the human component of the hand controls. He's able to adjust it to the length that he wants with our button compression. There, he gets it to the length that he wants. Everything's all set up. Then he uses the strap, puts it over the center, the steering console, and tightens up. He's ready to go.
So once the assembly is installed, it actually operates exactly like the previous device that I've used. And then both of those devices are very, very similar to the permanent hand controls that are permanently installed in my car. The only difference with this is that there's a little bit more play in the system, of course, because it's temporarily attached. It's not bolted into the steering column. But the gas and the accelerator feel is exactly the same. The handle's on the same side. The movement's exactly the same. I noticed no difference, which to me is the best thing in the world, because what I said I wanted was the exact same device, just quicker to install and uninstall. When it comes to uninstallation, you just remove the web belt, unclip it, and then you'll see I reach down, grab the ratcheting strap, and then slide it off the pedal. So it takes a process that used to take a minute 5 down to 27 seconds, I think.
So the most important metric of how well our design worked for this quarter was the time it takes to take off the pedals and put them back on. And we were able to attach the foot to the pedal in 32 seconds, which is down from 5 minutes previously. And we were able to do the whole process in 1 minute and 7 seconds, which is down from 8 minutes. So it's a pretty big reduction in time. And also we were able to disassemble quicker, just taking 27 seconds instead of 1.5 minutes. But the most important factor of this was that he was able to do all of this while seated in the car. And then looking at how we accomplished the goals that we set out for ourselves at the beginning of the quarter, we were able to meet all of our primary goals, most notably to reduce the time and have him seated in the car while attaching the pedals. But the one goal we didn't quite get to was fine motor skill, and that was mostly the function of the ratcheting mechanism that we purchased and used on our project. It's a little tough to use if you don't have the fine motor ability. Moving forward, we'd like to use a bigger strap to hold the pedal more securely rather than our little cable. Also, we could do some things with the foot and the material that actually attaches to the pedal that would give us a little more play and more secure on the pedal. But we've really enjoyed this whole process, and thank you very much.
Next we have Triple J.
Alright, so I'm James, this is Jeannie, and Jai. And we're Team Triple J. We're working on the Educational Design Kit for Children with Disabilities. So, to brush you guys up, you guys can see the midterm presentation. We're working with RAF, the resource area for teaching. And the purpose of RAF, or one of the larger goals, is to develop these innovative design kits that promote hands-on, multi-subject like teaching. And so the goal for us is to develop design kits that are accessible to children with or without disabilities. Because the current situation is that teachers with students with disabilities are kind of under-supported. And so what we want to do is provide affordable resources and options for teachers to support these classrooms and allow them to basically promote teaching, learning, teamwork, and open-ended thinking. And so to give you guys some more like bigger picture in terms of demographics, what we are focusing on are students with disabilities concerning motor skills. And so a large part of our population, or demographic rather, consists of children born with cerebral palsy. So about 0.14 to 0.4% of all students. And so in order to kind of accomplish our goals, we interacted with a lot of professionals in the field. We first got our goals from Greg Brown, director of RAF. He conveyed to us the goals of RAF, which are the goals that we embody, this type of things we're looking for. And we also talked to many other professionals in the field, Eve, Amy, Agnes. These are all tutors, instructors in the field who gave us hands-on experience. We also spoke with Alexander, thankfully pointed us in the right direction, helped us get the right direction. Also spoke with Stacy, a physical therapist, to verify and validate, make sure that the therapeutic aspects we are adding to our design kits are actually effective and what they use in the field.
So after those interactions, we learned from a lot of the educators that a lot of current lesson plans, they're unable to accommodate students with disabilities. So we're working on creating a unique and targeted lesson plan that's not only going to teach these students some engineering or math concepts, but it's also going to help them develop some daily living skills. So we're looking to bridge the gap between education and therapy. Some existing solutions, we talked about some of the RAF kits during our presentation, and those are some really great, amazing kits, but the limitations of those are that they don't have the therapeutic component that we're looking for to integrate into our kits. So some of our initial concepts and prototypes, we had a catapult design kit at first, and that didn't really have a therapeutic component also that we want to integrate. So we thought of a stirring game that's also going to teach students about like viscosity and fluids, and that would have the arm motion that we're looking for, but we decided to focus more on fine motor skills, which was something that a lot of educators told us they were concerned with. So right here is an image of sort of a CAD model of what we were going for. For our final design, we created a game that's going to emphasize, the first stage of the game emphasizes monetary value, negotiation, and teamwork. And we also have an engineering portion of the game where the students build a tower, and that will emphasize learning about force, gravity, design, balance. And throughout the entire game, there's going to be this emphasis on using fine motor skills. We're estimating that the entire cost of the kit is only going to be about $1 since everything comes from the bulk bins at RAF. And those are the types of materials that we feel are going to be really appropriate for the age range that we're targeting, which is 3rd to 5th grade.
So here you'll see, which we showed in the midterm project, part 2, phase 2 of our the 3-phase game. This is a tower building component, and you'll see it in greater context in the video that will come up. So one thing that we realized that we didn't have that was greatly needed, both for our instructions and for the teaching ability of the teachers in the classroom, because one of the things that we realized when speaking with Greg was oftentimes teachers get nervous or are uncomfortable with teaching new subjects or things that they may not necessarily be comfortable with. So one of the things that we wanted to include was a diagram that showed and gave a visualization of the flow of how our game will happen in lifetime. And one aspect that we wanted to take into consideration was our experience being California students in California classrooms. So small nuances like having a large number of desks to indicate that this game is appropriate and can be flexible for a very varying number of students within a classroom setting. So here we're going to show a game, an instructional video that details the flow of our game for a better visualization for you.
Okay.
The period inside YouTube. You know, it's supposed to be there. It's on the computer.
Wait, I saw the list on both. Yeah, it's right there.
Yeah.
Sorry, guys. I think for some reason. Oh. Oh, okay, since it's not working, we'll just talk a little bit about what the game is like. The first stage of the game, there's going to be a foam frame. You saw an image of it earlier where the students will put corks in it, and each of those corks have a different value for them. So that's going to emphasize the fine motor skills of the students picking up these corks and inserting them into these little holes. And after that, there's a point system, and the students will calculate how many points they get from these corks and trade them for what we call money, which are actually these little pens we got from RAF. And using that money, they can buy building materials with it, and those building materials are going to be corks and CDs. And using those corks and CDs, they're going to work together to design a tower and build whatever tower they want. So that was what the video was supposed to show.
We can just go to the presentation. Go ahead. So then our future plans are to finalize instructions with Raft and any other kind of packaging components that we want to add in. One of the things that we wanted to take into consideration was the presentation as well as the execution of the game, and so we wanted to definitely work with them to try to make it happen. And then finally, more testing and user iteration. One of the difficulties in the space that we worked in being in education is that we can't just like throw it into a classroom and interact with students ourselves directly within both the time scope and then also the way schools are nowadays. And so it's definitely going to be a trial and error kind of thing where we get it tested and get feedback and work from there. So thank you.
Power to the people. Okay, let me know when you're ready.
Hello, my name is Vincent Becerra. I'm a senior studying mechanical engineering, and today I'm going to talk about my project, Power to the People. So to begin, my grandmother, along with a large portion of older adults, experience varying degrees of arthritis. In my grandmother's case, due to her working long hours for 60 years, her fingers are bent and crippled. Yet she's still full of energy and vigor that she had when she was younger, and she enjoys doing many of the activities that she used to do. Among these activities is cooking. Yet, due to her arthritis, she is unable to open jars and carton lids to get milk or sauce or any other type of ingredients. Yet this problem extends to more than just my grandmother. In order to get a better grasp on the situation, I did some research on the Center for Disease Control and Prevention's website and found some startling statistics. According to the CDC, approximately 49.7% of adults 65 years or older reported an arthritis diagnosis. More specifically, 1.5 million adults had rheumatoid arthritis in 2007. After deciding on a specific problem and I was attempting to solve, I then set about setting design criteria for my tool. What I came about with was as follows. The tool must be designed so that it can be operated by my grandmother and others with varying degrees of arthritis without any outside assistance. It must be able to be used on lids of varying sizes. It must be able to be operated without using without using an excess of force that might not be provided by the user, and it must be portable and inexpensive so it can be used in different kitchens or areas. And so after looking at the design criteria that I'd set in mind, I then went about and did some interviews with the users. Because I was attempting to make a tool that could be used for varying degrees of arthritis, I decided to interview 3 people. First up was my grandmother. Here's a picture of my grandmother's hands to showcase how severe her arthritis is. My grandmother is 75 years old. She works 60 years in the field and factories, and she has 9 grandchildren that she takes care of every day. Yet she still cooks 3 meals a day, 7 days a week. Unfortunately, when she is cooking, she does need outside assistance to help her open lids, like I was saying before. Because of this, she is in dire need of a tool so that she can continue cooking without any external assistance. The next person I interviewed was my father. He's 44 years old, and as you can see in this picture, he has the onset of arthritis. He works on a computer all day, and that coupled with the family history of arthritis has led to this onset of arthritis. Thankfully, he is able to open most jar lids with relative ease, although there is the occasional lid that comes into play where he does need to use some type of assistive tool, such as a grip rack. The third person I interviewed was myself. I'm 22 years old, relatively good health. I do have the family history of arthritis, but it hasn't shown itself yet. I can open most lids pretty easily. An occasional lid will pop up where I do need help, and in this case, I feel that it would be helpful to have some tool that I could use to help me with that. After doing the interviews, I then began looking around the market to see what was already out there. I found a bunch of different devices that could be used. Unfortunately, none fit the criteria I had set for myself. In case in point, this one is an automatic jar opener, but it is far too expensive, retailing at about $250. This tool calls for a strong grip to get a tight seal around the lid. This one requires the user to really jam the lid in there to get a good seal. This one right here, it requires insulation, and so it's not portable. And these jar grip rags don't add any help to the torque situation. So after finding out that there was nothing on the market that could help with my problem, I then began ideating to find different solutions to this. Most of my ideas could be factored down into 4 categories: heat, friction, force, and pressure. After going through many sketches, I decided that due to safety, feasibility, and price, that my best bet was to go with the area of friction. And so with that decided, I drew up schematics for my first design. Here's a picture of it, and here's a zoomed in picture. So as you can see, this allows the user to, this handle allows the user to extend it and retract to get a better torque. And these little notches right here are where the band will loop through, allowing to get that tight seal on the other side of the lid. So once with the design in mind, I went in and using the ProJet printer, I 3D printed the part. And here's just a couple pictures from the fabrication process. Here's the piece on the plate that it was printed on. Here's the excess wax melting off, and here's the finished piece. Now, after I got the part printed, I began putting it through a variety of stress tests to really see how it worked out. The biggest one was just me putting as much force as possible on the handle to see if it would snap. I put as much weight as I could on it, and I couldn't get it to bend. Thankfully, it did retract because of the plastic, and so it worked fairly well for what it's being called for. Unfortunately, I did find 2 design flaws. The first one I found relates to durability. I was playing around with it one day, and I dropped it, and it fell on its little U-shaped part, and it snapped. And the reason was because of these slots I had cut through for the band. They had caused the wall to be way too thin, and so once a little force was added to it, it snapped. The second problem was with elasticity. The DISM was way too thin to be used on its own, so I decided to use a rubber pad that cut into strips to reinforce it. Unfortunately, while this did add more elasticity, it still ended up snapping. So with those 2 problems in mind, I went back to my SOLIDWORKS file, made some corrections, and this was the second product I came out with. So as you can see, I did make the initial handle a little bit longer. After doing a little bit of testing, I found that I needed to retract way too much to get any good force. So I found that this length, which was 7 inches, allowed my grandmother to use it without having to use the pull-out function. But I like the pull-out function, so I add that in for anybody who had a more severe case of arthritis than my grandmother. Additionally, I changed the 2 double slots to 1 slot and thickened the walls so as to not break when I dropped it. And so with that in mind, I went through the fabrication process once again and came out with this final product. And I set about doing various tests on it. I did the same stress test trying to break it. I dropped it a couple times. I started slamming it against the walls. I did everything I could to try to break it, and thankfully it worked. And so after that, I then went out. I got a much thicker a much thicker band made of rubber that wouldn't snap when pulled, but at the same time, it did allow to get a tight seal around the lid. With that in mind, I went out, bought a bunch of cans, and started testing it out myself. I was able to do it pretty easily, and I took it to my grandmother, and she was thankfully able to use it. And so for what's next, because it's a SOLIDWORKS 3D printed, it's easily replicated. The cost was fairly cheap. It was under $30. It could also be customized. I just have to go in and change it on my SOLIDWORKS, and I'm looking forward to presenting the final product to my grandmother in a couple of weeks.
Okay, we'll just take a few minutes break to stretch. And anybody who has an issue who hasn't signed in, please do that now. If you haven't signed up for food, now's a good time to do it. So we'll just take a few minutes here. Breather.
I just saw it.
Do you want pudding?
Are you in a good mood all of a sudden?
Let's get going together. Let's actually what we want to do. Okay, our next group is Far East Entertainment. Take it away, Far East.
Hi everyone, my name is Michael Vela, this is Suki Gulati, and this is Andrea Stein. Together we are Far East Entertainment, and we will be presenting our project, Progress Visualization for At-Home Therapy. So let me just run you through the agenda quickly. We're going to start with a problem statement, then we're going to talk about our need, then we'll look at the market research that we did, some of the past concepts that we explored, prototypes that we actually built, the final design visualizations, and then where we hope to take this from here. There isn't a question section. Sorry. Okay, so physical therapists often recommend users to do exercises at home as a continuation of therapy. The issue with this is that a lot of people find it very difficult to motivate themselves to adhere to these at-home therapy regimens.
With this problem in mind, we consulted with our project suggesters in order to begin the need-finding process. We spoke to Eric, who jump-started our process, and Debbie, who provided valuable insight to the need, as well as connected us with some of her former clients. We interviewed some of these clients, and we especially targeted the ones who we thought might benefit from an increased motivation to the at-home therapy situation.
We found that at-home therapy relies mainly on a person's intrinsic motivation. And while most people were determined to regain certain functions like walking, they found it, or they tended to focus a little less on functions like posture and hand mobility. And a lot of this was due to the difficulty in visualizing progress. So we started to research the market. The first exposure we had to what was on the market was Eric Medine's stroke therapy game. We found it to contain certain positive features that we identified as being key in capturing a user's motivation. And so we decided to use this as a base for our design process. We then broadened our view to the rest of the market and found a list of different products. These are some of them. So the 3 examples listed up here are examples of products that are being tested for stroke therapy specifically. Some are games and some are tools, but none of them hit the mark in terms of presenting an intuitive visualization of progress. For this reason, we used Eric Medine's stroke therapy game as inspiration for the direction we wanted to take with our own project.
Looking into this, there were a couple concepts that our market research led us to think would be good ideas that we actually didn't even end up prototyping. We explored most particularly the Myo armband and Leap Motion as potential hardware devices that we could use to facilitate our stroke therapy game. We found these devices to create artificial limitations that were simply not realistic for therapy. The Myo armband armband, for example, was almost impossible to calibrate, and for the leap motion, your hand has to be within a very limited range. Other things we did not prototype, as you can see here, we actually went with the hat idea, but ended up not designing the belt because the sensors that we used didn't lend themselves well to a lower center of gravity, and we found that that data was not accurate. After talking about what we did not prototype, let's talk about the prototypes that we actually did build. From a software perspective, we wireframed up prototypes for computer, mobile, and tablet devices. In the end, we decided that based on those wireframes, we should go with an internet-based game, and our game is currently computer-based. We thought this was best because web apps can easily be ported over to mobile or tablet devices, but it's not exactly the other way around. From a hardware perspective, we tried a couple of different drivers. First was the Arduino Mini and the Arduino Uno. We decided on the Uno because while the Mini was more compact, it required more extensions to be able to be plugged into a computer, which negated the benefits of its compactness to begin with. From a sensor perspective, we debated between a gyroscope and accelerometer or a tilt sensor. We decided on the gyroscope and accelerometer because it allows us to customize and calibrate sensors, whereas a tilt sensor was just a binary yes or no value that didn't allow us to account for individual users.
So let's talk about our user testing. For our user testing, we conducted 3 rounds. For each user, we ran a calibration round, followed by 2 test runs. So for the first test, we asked users to not focus on their posture, to not worry about it at all. And for the second test, we asked them to focus specifically on their posture. So these are examples of some of the tests that we ran. This picture right here is an example of us running a second test on a walking therapy. So we asked our user here to walk up and down the corridor, not focusing on posture and then focusing on posture. And then over here is Jackie, another one of our user testers. We asked him to do a sitting calibration. Once we did the calibration, we asked him to do an arm lift exercise while maintaining his posture in the same position. Our main findings were not what we expected, but were very, very beneficial for us in terms of designing our final prototype. And I think the main takeaway was that what seems intuitive to us isn't necessarily intuitive to our users. So the first thing being the visual reference was not intuitive enough for our users. We initially put our representations in numbers as percentages of how much of the time was I leaning to the left versus the right, or front versus back. But our users told us that they wanted to see a more visual representation of this, so maybe a chart. Another feedback was that longer calibration was needed. This was actually an observation on our part. We noticed that we needed to calibrate for longer periods of time in order to make our sensor more sensitive to the specific exercises that our users were running. And that also led us to the next insight, which is that different exercises require different calibrations. So a person's posture can be different if they're sitting down and when they're standing up. They might have better posture when they're sitting, for example, which is the case for one of our first user tester. And then finally, something kind of a little more trivial was that we didn't use an adjustable hat to start with, which was a little bit of an oversight on our part.
Yeah, so we incorporated many of these suggestions and findings into our newest iteration and focused on 2 main features. The first is affordability. We were able to manufacture our product for under $70, which we found pretty exciting. Second, we also iterated to increase usability by making the user experience very simple. The wearable itself is cost-effective and is customizable to adjust the calibration settings. Like Mike said, you can adjust it for when you're standing or sitting, so depending on what exercise you're doing, you can decide which calibration setting to choose. The game itself is also interactive, and there are opportunities to involve family and friends. Moving forward, we want to think more on things such as the device's durability, transportability, and technological accessibility, such as the fact that right now it requires internet to function.
Let's walk you through the current iteration of our prototype right now. This is a hat that we used. As you can see, none of the wiring is exposed, and the sensor is actually the only thing exposed on the duckbill of the hat. This is what we had users wear, and after the initial calibration stage, as long as they are using the hat, we have a 10-foot cable that we ran to the computer. As long as they were using the hat, all of the data was automatically logged, recorded, and processed by our software. In order to visualize their progress, they simply navigate to the companion website in a normal web browser. As you can see, we decided to go with a simple design, no complex graphics or animations. We wanted to highlight the 3 core features of the site. To upload the data, they simply choose the file that we automatically generate and click the Add Data button. Our software does all the work for the user by automatically interpreting and parsing raw roll, pitch, and yaw data into human-readable charts and percentages of how much they lean in any direction or whether they're leaning at all. And the fun part is that all of this visualization and progress allows the character that we showed on the home screen to grow with them and actually learn games that they can play with the user. Here's an example of a game we programmed. It's just a simple arcade type game where you go around in a low stress environment and collect all the stars. And the more that they use the device, the more games they unlock for themselves or their grandchildren to play because the character is actually growing with them. While moving forward, we really want to make this data transfer wireless. We want to make the hardware smaller, and we want to make sure that there are multiple accounts so that their grandchildren, for example, could log in and have their own unique experience.
Next, we have Disability Heroes.
And then which is it passages? We are the Disability Heroes, and we are working on an educational design kit for children with disabilities. I'm Alessia.
I'm John. And I'm Cassie.
So the resource area for teaching would like to introduce an educational design kit, a new type of hands-on, open-ended, multi-subject kit for teachers to use to stimulate learning, teamwork, and creative thinking in classrooms. Next slide. The main problem is that the educational design kits need to be accessible to all children, both with and without disabilities, to engage them in learning, teamwork, and creative thinking. As you can see here, there are over 5 million students with disabilities between the ages of 5 to 17 in the United States. So our goal is to therefore explore ideas for a kit that will engage children, including those with moderate sight, mobility, or dexterity limitations, and evaluate their effectiveness in a classroom setting. Next slide. The main design criteria for our kits is to promote learning, teamwork, and creative thinking. The kits must be low cost and safe, and more importantly, appropriate for the disability level of the students. So we had a brainstorm session and we came up with over 40 ideas, and we had to narrow it down to 3. And we did this by using a design criteria analysis where we rated everything from 1 to 5, and we came up with our top 3 choices.
And from our top 3 choices, we created 3 prototypes. And this includes a physical prototype and a lesson plan. Next slide. From there, we had to refine it a little more. And we used another rating sheet, but this time we used it in terms of disability, specifically orthopedic impairment. And based on these ratings, the square wheels rolling and sundial were the most accessible. Next slide. Throughout our whole process, we also did a lot of interviews. First of all, of course, Greg Brown, the Director of Education from Raft, was extremely helpful throughout the life cycle of the project. Also, Xochitl Quetzal-Davila, the Regional Director of Achieve Learning and Resource Center, helped us figure out how to make the project very accessible and to increase the openness of the activity for all students. And Eve Sutton, an educational consultant, made sure the project was very applicable to the classroom and the needs of the teacher. Next slide. We also interviewed Amy Kraus, a special education teacher in Palo Alto, and she made sure that we had more of a plug-and-play lesson plan to give to the teachers in the end. And lastly, we interviewed Sandra Orozco, a social worker, and she helped us assess the psychological impact of our activity and how to make the children feel included in the activity. Next slide. And now for our final 2 deliverables. We ended up doing 2 instead of 1 because we kind of fell in love with the ideas. Next slide. So first is the sundial. And for this, we asked the students to imagine they live in a time before clocks, and they have to use the sundial to keep track of time. This is just, the last slide was just some pictures of the activity. We did this throughout the afternoon to show the measurements that the students would have to take. Next slide. We tried to use low-cost materials. As you can see, there's only 3 different materials for the sundial to keep it simple. We also have this applicable to grade 3 through 8 through a variety of concepts, including history of timekeeping, the Earth's place in the solar system, and empirical data and prediction and estimation. Next slide. We also came up with our idea sheets, which in Raft is pretty similar to a lesson plan. So this outlines how to set up the activity, the different steps and discussion to go through for the teacher, and also some additional learnings the teacher can do to extend the activity a little further. Next slide. We also did a quick cost sheet of how much this would cost. This is all based on Raft prices and the bulk bins. And as you can see, one kit only costs 55 cents. Next slide. And the most important aspect of this project is how it is accessible. So on a variety of levels, we tried to make sure that this activity could be completed without the use of one or both hands and only with elbows. Also, we tried to make sure that's an observation-based activity, so you don't have to be super hands-on for students who aren't able to. We also have the option of using tape or Velcro to hold down the objects, because sometimes students accidentally move them when they have a motor impairment. Also, the project can be completed on a table, because students with muscle impairments have sometimes a hard time getting on the ground and back up. And there's also an opportunity to take breaks in between measurements. Next slide.
So our second educational kit was making square wheels roll. For this exercise, the students were basically told that they lived in a city where vehicles and bikes only use square wheels, and they had to come up with surfaces that would allow for those wheels to roll smoothly. So here are some of our raw materials that we used. That's some of the prototyping process. That's a snapshot of our prototyping process. Again, we used materials from the bulk bins, and so they were low cost, just chocolate holders, file folders, plastic sheets, foam, pencils, and a carpet square. Curriculum topics we hope to cover include pattern recognition, engineering and design, brainstorming principles, and teamwork principles. Similar to the first educational kit, our idea sheet essentially is a guidebook for teachers, or a guideline for teachers before they sort of embark upon actually conducting the activity, which includes prep for any students with disabilities, all the students as a whole, which includes, for example, taking those chocolate holders and cutting them up, because we don't want the students working with scissors and things like that. We did another cost evaluation for this project as well, and it came up to $1.25. Again, pretty cost efficient. Prices might go up based on, if like they scale it up, the prices go up. But even then, we predict that it's still going to be below $2, which is great for a teacher who has about 15 to 20 kids. Again, we designed the square wheels kit for students with orthopedic impairments. We fashioned a handle that the square wheels could be operated with, which is also a universal design principle, just because we tried using the square wheels and it was easier with the handle anyway. What we did do, however, was provide the opportunity for teachers to vary the width of the handle so that different students with different limitations could sort of have the wheels customized to their abilities. In terms of limited motor controls, we suggested that teachers use tape to stabilize the surfaces. And finally, in terms of limited physical strength, all of our materials are really lightweight. They don't require much force, and the projects can be completed on tables. Most importantly, the teaching plan includes bits when there are discussions and like classroom discussions and things like that that sort of offer breaks between physical exertion throughout the activity. In terms of future work, we highly recommend that both these activities be conducted with students overall and students specifically with orthopedic impairments, and the idea sheets be reevaluated based on the feedback from these activities. Eventually, we hope that the kits will be posted on the Raft website after the vetting process, and a display will be set up to demonstrate our Raft kits. But please join us on Thursday for Demo Day. We're really excited to show you guys our kits, and thank you.
Okay, next we have Led Zeppelin. Hope you brought your musical instruments.
Hello everyone, I'm Justin, this is Sarah and Joaquin, and we are Team Led Zeppelin. So this quarter we worked on a project with a company called Wheel, who's a startup from Japan, on this enhanced visibility project. So you might ask us, what is Wheel? Well, this is the Wheel. It is a all-wheel drive, all-terrain, personal, next generation personal mobility device. It's gathered great critical acclaim from blogs and magazines such as the Wall Street Journal, The Verge, and Wired magazine. And basically, it's one of the hottest things on the market now. So with that in mind, like what do we have to do with Wheel? What can we contribute to their amazing product that they've already had? Well, take a look at a corner of a busy street on San Francisco. So you can see here, everything's well lit. You can see crosswalks and people, going about their business every day. But at night, however, it becomes a traffic jam, and it's places such as various corners become very dimly lit, and basically people who use wheelchairs or personal mobility devices or power chairs, they have a very, very difficult time going about their business without, say, getting into a car accident. And this is a major problem that we're trying to fix. So, in order to basically develop the system, we realized that we needed the system to tackle two essential needs. We needed it to ensure that wheelchair users can travel safely at night, and also ensure that drivers are able to see wheelchair users. So. Before we started our project, we looked at existing solutions. Many people have attached bike lights to their personal mobility devices or power chairs, and a lot of people have also used headlamps. People have just worn these lights on their heads and they go about their business. But unfortunately, both of these are not very optimal. They're not integrated with a wheelchair, and you have to carry it around. And with this beautiful device, the Wheel, it would break the design aesthetics if you had to have a separate device. So, where did we take our inspiration when we tried to develop our enhanced visibility device? Well, we decided to look at the automotive industry and look at how you have different headlights and side lights on various parts of the car, and we decided to use this as our initial inspiration for our project.
So with these inspirations in mind, we came up with 3 main design goals that we wanted to incorporate into our product. The first is illumination, mainly forward illumination, so that wheelchair users are able to see their path in front of them, so that they'd be able to see obstacles like cracks in the sidewalk or uneven pavement. The next design goal is visibility, so that other pedestrians or drivers are able to see the wheelchair user when they're crossing the street at night. And the last one is a coolness factor, and we wanted to be able to integrate our design with Wheel's already very unique design, and we also wanted to add a light show just to add a little fun component to our design. We also had a couple other considerations with safety and comfort. We didn't want the design to be distracting or the brightness levels to be blinding to other people, and we wanted a really non-intrusive design that was well integrated into the current model.
So we started prototyping, and you saw this at our midterm presentation. We decided to go with RGB LED strips and also just plain white LED strips. These are very easy to use products for quick prototyping, and also are very bright and low power, so they're very energy efficient for a battery powered device. And so this is our first iteration of our design. Got a white headlight on the top over here, some side lights and front and back lights for color with RGB strips. Power system, electronics, and Arduino controlling it, and a battery on board. Some testing at night. It was basically really dark at night, and with our small headlight, we could light up the entire area in front of me, so it was very effective, I guess, at making it visible when I'm riding around in the wheelchair. I've seen my foreground, so that was a nice thing to see. And also, when put together, it's a nice visual effect with your color LED strips and also the headlight together on the side panels of the wheel.
So, as we kept on developing from this initial prototype that we showed you at the midterm, we decided that we wanted to build customized housing that would seamlessly integrate our LEDs with the existing parts on the wheel. So we decided to use heat bending as our process, and we basically used white matted acrylic and basically heat formed it over the existing parts, so that you can, as you can see over there, it covers the LEDs very seamlessly. So we spent a lot of time looking at, understanding how to take apart the existing product and integrating our LEDs with the wheelchair. So you can see here kind of the little process of taking it apart, and you can see Joaquin here stooping over and putting it in. So you can kind of see here, it looks, by using this acrylic and heat forming it to the existing parts, you can see it's seamlessly covering the LEDs over the wheel. And you can see this is what it looks like when it's lit up. You can change all the different colors, and basically it looks as we initially planned it to.
So with this final prototype, we took it out at night to test and see how it would look. We have a short video. And basically what we did when doing this testing was we left one side of the wheel, we put one side of the wheel with our current panels so that they had the LED strips on there, and then we left one side barren so that we would be able to get a direct comparison between non-lit and lit. So this is the current wheel model. There's a small LED on the back, which you can see in red, but it's not really enough to get good visibility. Yep, this is the side without any lights, and so he's crossing the street here, and it's dark at night, and you really can't see what's happening. And on the other side, you're able to see the illumination on the foreground as well as some on the side, and it's just really clearly visible and bright. And we also made the brightness level adjustable, so you could tweak that if you wanted to. Here's some more testing in the main quad. It was really fun to do. And so after that testing, we really liked the current prototype that we had. And so for the demo day, we're planning on mounting both sides with the LED panels. And here are some comparisons. This is the front of the wheel. This right side over here, you can't see, there aren't any LEDs and you can't really see what's going on, but we have on the left side our panels, and that's from the back view. You can see that the lights on the side are also visible directly from the back. And here's just another side-by-side comparison of what it looks like with and without LEDs. And you guys can check that out on demo day.
So I guess in the future, we'd like to explore different manufacturing methods such as vacuum forming to better incorporate the LEDs and better create housings that can fit these parts onto the wheel. So we'd like to use vacuum forming, maybe, and eventually be injection molded. And we'd also like to fully integrate our hardware into the wheel, of course, so then maybe someday you'll see these amazing machines with our product inside. And then lastly, we'd also like to incorporate some Bluetooth control of it in a smartphone app that will also go with the wheel, so that anyone can easily control the brightness or the color of the lights as they're going about riding the wheel.
We'd like to thank Dave Jaffe for teaching the class, Fernanda for presenting the project to us, and also the team at Wheel, for Natsa, Tian, and Chris for helping us out the reporter. Thank you.
Thank you.
Okay, last but not least, we have the caffeinators.
Hi everyone, we worked on the Knee Extension Assistance Project. I'm Susan and this is Marshall. We're the caffeinators. We'll be going over background, some research we've done, brief overview of our prototyping and what the current state of our prototyping is, and also what our plans are moving forward. So this is our team, us two and our project partner, Max.
So Max, when he was a kid, was hit by a semi when he was riding his bike, and as a result has a pretty messed up right lower leg, knee especially. But nevertheless, he's still extremely active, does a lot of sports, he lifts weights, does CrossFit, runs, snowboards, swims, does all kinds of crazy things. So because his lower leg and his knee are kind of the limiting factor in a lot of his activities, he's looking for a way to kind of increase the power output, especially on the extension of his right leg. Hence where we come in. Here's kind of for reference, Max's knee on the left and a regular knee on the right. So there's a lot of missing bone, missing muscle. He's missing 2 of his quads out of 4, among other things. So he has kind of a lot of orthotic things that he uses already to help cope with his knee problems. And we're just helping integrate with some of his existing braces and methods for exercising and working with his injury.
Great. So some of the research we did was based on current products. Originally, we just set forth and looked at exoskeletons, so like Rewalk and the Exobionics exoskeleton. Realized that was way too complicated, especially for the scope of this class. And so we focused more on things that just provided the extension assistance. So something like the Bartlett tendon and other orthotic devices. What we realized partway into our research was that we could also focus on materials research. So we looked into various elastic materials such as polyurethane and just bungee cords. One of the challenges with that was to figure out how to attach it to the current brace, since we wanted to minimize the amount of modifications we made to his current brace. We also talked to Gary Burke, who's an orthopedist here at Stanford, I guess, and he provided us with more detail on like what's actually been done and like kind of pointed us to the right direction on other materials to research. And here, this is a picture of us visiting Max's orthotist at UCSF, where we saw like what their process was in making the orthotic devices. And another source of our research was just Max himself, because he's played a lot with his own brace and also like what works and what doesn't work. And with every round of prototyping, he would take it home and just like test it out and send us emails like, here's my impression of how it works, and here's what doesn't work, here's what fell apart, and here's what you should improve on. So that was also like a good source of feedback.
So getting into our prototyping, this was our first extremely quick and dirty kind of concept idea of what we wanted to eventually look like. So having some kind of elastic band that stretches over the knee such that when the knee is bent, it's kind of it elongates and then wants to snap back to being straight. And this was just a Room 36, whatever we could find laying around there.
Our next prototype involved trying to have hardware so that we could test out different materials really quickly. So the way these bungees are attached are by just a simple clamping force with just 2 plates and screws.
And then experimenting with some more materials, we used a rubber tie down that you would use to tie something down with a truck. And ultimately kind of figured that the bungees were working better than even though this is much thicker and much stiffer seemingly, we had better success with the bungees due to kind of the sleeving on it having lower friction over the knee joint and the pulley. And here are also some clamps that we designed such that instead of having to drill a hole in the brace or use an existing hole, we could just clamp onto the metal upright that you see running down the brace and have some kind of adjustability up and down the brace.
Right, so this is where our current prototype is.
So this is Max actually in his gym, trying it out, doing a little deadlift. So you can see it's disconnected to begin with, and then you can just snap the bungee cords into the bottom clamp, and then stretch it over the knee. Then he has some assist to his extension. then once he's done, you can step back and just pop out, pop it off the knee, and then pull the bungees out, and he's back to normal.
Yeah, so I guess as you can see, our functionality goals were to have aid with the knee extension and also so that he could use it every day and just be able to switch it on and off, so to speak, really easily. So we also wanted it to be adjustable, so you can pop in like any length of bungee or like, I guess you can pop in like any length of bungee and then adjust like the force that you're given for the assistance. And also we wanted to keep it as simple as possible for the user. So I guess for next steps.
Yeah, so moving on, this is actually a picture that Max sent us when our current pulley had a bad habit of unscrewing itself. So it backed itself out of its threads and kind of rolled off underneath the motorcycle in the street. So moving forward, it's getting rid of problems like that. And we've figured out some solutions to that with better fasteners and kind of designing the pulley such that it can rotate relatively freely instead of being attached to more or less attached to the fastener. And pretty much making everything smaller is our ultimate goal, more streamlined, easier to put his pants on, for example. And using other bungee cords, so we use bungee cords that were available at Home Depot and Route 36, but we realized looking through kind of the master catalog and other places that there were lots of other diameters and kind of sizes of bungee that we could play with, and we could buy, for example, a whole like 50-foot spool of bungee if we wanted to make a series of different lengths and different attachment mechanisms. So that's actually coming tomorrow, just in time for demo day. And for the collars, the the quick release mechanism in the prototype that was in that video, there's an aluminum block which has little slots in it for bungees, but making it so that we can use different sizes of bungees and kind of incorporate a better release mechanism rather than it's not ideal how it functions right now. It rubs a little bit too much. So we were playing with heat forming some polycarbonate collars such that it can it's like you'll see it on the next slide actually. On the far right, it's just kind of a C shape, and then when you tie a knot and have a ball end on a bungee cord, it'll just slot into that shape. This is just a progression of our collars from the simple clamp type to ones with slots in it for the bungee to fit through, and then ultimately what we're hoping to use a kind of more of a collar C-shaped thing that it can slot into and be really well set in.
That was fantastic. I'm really blown away by how well everybody did. If you're really interested in seeing these projects up close, come by on Thursday and have the whole class section walk around and see a bunch of car and ask questions about all those projects. I want to thank the students once again on their efforts and excellent results. So thank you very much. On the desk. I'll pick them up and see everybody on Thursday.